All right, let's do a quick summary of the Test 3 material, and we'll start with a recap of what's important from Test 2. So basically everything that we did on Test 2 about p-values and confidence intervals, that's still relevant here. So remember, with a hypothesis test, we're always collecting evidence against the null and for the alternative. So on Test 2, we talked about the null as being like no change or no effect. On Test 3, a lot of the time it's going to be useful to think of the null hypothesis as no relationship. Okay, and then the alternative, that's where you put the claim that you're trying to prove. For this test, a lot of the time it'll be that there is a relationship. The things we learned about p-values still apply too. So when your p-value is small, that means you reject the null hypothesis, you've got sufficient evidence to conclude the alternative, whereas the p-value is large, you don't reject the null, you don't really have enough evidence to draw any conclusion. So one of the more challenging aspects of this class is trying to decide which sort of methods are appropriate for which situations. So I made this table to kind of show you how it all fits together. The ones that we're going to be talking about on Test 3 are the 2 chi-squared tests and linear regression. So the way you read this table is that you basically pick a test by classifying your response variable and your explanatory variable if you have one. Okay, so you notice that the chi-squared tests, these are for when you have categorical data. And the 2 different types of chi-squared test, a goodness of fit test is when you have no explanatory variable at all, right? So you just have one variable and you're asking a question about the distribution of that variable. A test of independence is when you have 2 variables and both of them are categorical, right? Both the explanatory and the response are categorical. That's going to be a chi-squared test of independence. Okay, regression, that's about relationships too, but that's where you have the relationship between 2 variables that are both quantitative. That's when you do regression, and if you want to do inference, you're going to be looking at the t-test for the slope. So let's start by going over chi-squared tests. So we said that chi-squared tests are when you have categorical data, and we've got 2 different types. So a goodness of fit test is where someone makes a claim about the distribution of a categorical variable. So notice this is singular. We're talking about one variable here. That's when you do a goodness of fit test. And the question is the proposed model a good fit, or does your sample provide evidence that the proposed distribution is incorrect? So the example that we saw in class was whether or not the distribution of housing choices at UGA as a whole applies to MSIT 3000. So we have this distribution that applies to UGA as a whole, and what we're trying to prove is that MSIT is different. So in other words, at least one of these proportions is different from what's been proposed here. Right? So that would be an example of a goodness of fit test. A test of independence, this is whether or not you have evidence of an association between 2 categorical variables. So the null hypothesis in this case is that the 2 variables are not related to one another. So knowing one doesn't give you any information about the other. And the alternative, the thing that you're trying to prove, is that the 2 variables are related. These 2 types of chi-squared tests, they both have the same conditions. So you need to have a random sample. We've talked a lot about that, so I'm not going to go into more detail here. And you need to make sure your sample size is large enough. So we've always had a sample size condition, but we're going to check it a little bit differently here. The thing that you check is based on the expected counts. So specifically, you want to make sure that your expected counts are all at least 5. Okay, so let's get to the calculations for chi-square. So the formula for the chi-square statistic, that's given on your reference sheet. And notice it's in terms of the difference between the observed and the expected counts. So when we say observed counts, we're talking about your actual data, right? What categories do your actual data fall in? And then the expected counts, we're talking about what we would expect if the null hypothesis were true. Right? So basically, if you have a large chi-square statistic, that means there are big differences between your actual data and what you would have expected if the null hypothesis were true. So in other words, when your chi-square statistic is large, that's going to give you strong evidence against the null hypothesis, right? Because your data are not consistent with what the null told you to expect. So to calculate your p-value in JUMP, of course, you're going to choose the chi-squared distribution. Notice for the probability option that I've picked greater than. Whenever you're doing a chi-squared test, you're always going to pick greater than here. And then for the degrees of freedom of the chi-squared distribution, it depends on what type of test you have. So this is given on your reference sheet, the formulas for the degrees of freedom. So again, it's really important, first of all, to figure out what type of test you're doing, and then you can use the information that's given on the reference sheet. Okay? So you can draw a conclusion based on your p-value, but remember, your conclusion is just going to be that at least one of the proportions is different. And that's not always a satisfying conclusion because you might want to know which proportions are different. And that's where the residuals come in. Okay, so if you have a positive residual, that means that your observed count is greater than your expected count. Whereas if you have a negative residual, that means that the observed count is less than the expected count.